Hello, this is Ganesh Manjunath,
Hi, this is Kritik Narasimhamurthy.
and this is our final FPGA project. This is a group project where the aim of the project is to design and implement a complete hardware software system that performs AES-128 bit encryption and decryption. The system responsibility is split between the HPS and the FPGA. First let's open up our platform designer where we have created our custom module. After opening platform designer, we have to load our .qsys file. So as you can see, we have added our custom AS module. So yeah, you can see here that the module is added. And you can see that the um, addresses are mapped. Coming here, you can see that the connections are done to the LWAXI master bridge so that the software can read and write registers using the memory mapped IOs. In the address map, our AS peripheral occupies a small region, and the interface signals are address, read, write data, read data, and byte enable. Let me just try to show you the block diagram. So yeah, here you go. This is a complete block diagram. Yeah. So in order to create this, custom module, so first we have to go under File, a new component, give the name to a new component. This will generate a block symbol, and under Files, we have to add our .v or .sv or whatever synthesis files that you're adding here, and here you have the option to analyze the synthesis files, which will in turn give you the modules present in the files, and you can select the top module here. So after doing that, you'll check the parameters, I mean if you want to add any, and you'll check the signals and interfaces. So in this part we had to add a reset signal properly because for some reason it didn't add up, and we had a error. So after adding a reset signal, it was proper. So yeah, so as you can see, after adding our custom module, we map the clock to clk0.clk, and so does our reset is also mapped to our clk.reset, and the avalanche slave is mapped to the LWAXI master. So this forms the half bridge, and the addresses are shown here. Yeah, so after this you'll go and under generate and generate the HDL file. So yeah, let me just close this up. After generating the HDS file, you'll get the .qib file generated. So under which you can see that the system is here, and you can verify is the if the module is added here. Okay, let me just go and search. So yeah, here are the four signals that are connected. Yeah, and let me just show you the .svs.sv file also. Yeah, we have added a system verilog file. this is our module AES Axle Avalon. So yeah, it exposes a simple register map for our 32-bit keywords, which generates four 32-bit plain text as well, and four 32-bit ciphertext words. All these are words. When this software writes start, onto the in control, the wrapper generates a one cycle start pulse, sets busy, clears done, and waits for the AES core to finish. When the core asserts done, we latch the 128-bit ciphertext onto the output registers and set it as done. So this is how the hardware is working. And yeah, after doing this, we'll set our top module here. It's this file wraps the all the modules all together. Yeah, so we'll set this as our top module and we will compile. As you can see, the compilation is done. And so this is our fitter usage resource usage summary, and as you can see, all the details are here. So yeah, after the compilation has run, you'll go under tools, launch the programmer to program our FPGA, and wait a second. Yeah, you auto detect. Yeah, and you load the SOC file here, and you'll click on program and start programming. Yeah, now the FPGA board has been successfully programmed. Yeah, after programming the FPGA, you can see that the FPGA is programmed properly, and we have mounted our USB as well. So just to show you the outputs from uh, PuTTY terminal, just make this. Yeah. Now, since the FPGA program has been programmed with the .sof file, now we have to look into the software part. So that means here is our .c code, and yeah, so we have to compile this for ARM cross compilation. So we open up the terminal, uh, yeah, and we go to the directory and make sure that the compilation is done properly. So when I do ls, you must be able to see four files here. Let me just clean it and run it again. And now I'll just compile it using my makefile. And as you can see, now the compilation is done and it has generated the required file. So yeah, now we need to mount this AES dot underscore test file onto the FPGA. So let's mount that. In order to do that, I've installed PuTTY. We'll create a connection here using COM9, and since the FPGA is already running, it should be able to communicate right now. Yeah. So yeah, here we go. Now let me mount the disk. I think I have mounted it already, but let me just to make sure, do it again. Oh yeah, it's already mounted since the USB is already connected to the FPGA. So yeah, let's copy the file. Let's copy the file in media USB folder fpga AES.test. Copy the file to root. Now, if you do this, you should be able to see this test file here. Yeah. Now let's do chmod. Yeah. Now I think our C code is compiled and it's ready to run the code. So let me just run the file. Yeah, here it is asking us to enter the plain text and the limit is 16 characters. So let me just enter my name and my group project partner's name and click on enter. So as you can see, I've added test to make sure the address bits are updated properly. And this is the HPS generated uh, encrypt key. And now the HW address bits are confirmed here that they're updated. And the original plain text in ASCII characters are this. And I'm just adding in a statement to print the hex values as well. And here it is again confirming if the registered are updated. So I've added these console statement just to make sure that the hardware and software integration is happening smoothly without any flicker here and there. And as you can see, the ciphertext from FPGA is this, I believe. Yes. So yeah, after this the plain text from FPGA is this, and as you can see it matches our original plain text as well. Plain text from FPGA, and here it finally it passes the validation as well. So as you can see, the HPS and the FPGA systems are working as required. Whenever we enter the 16 16 characters, it is the data is getting encrypted and by the HPS and FPGA, and then you can see the result in ciphertext. And then when you convert that to plain text and see here, it's the same as what we entered. I've also added some validation test cases. So what if you enter characters more than 16 digits, let's say 6, 7, 10. So obviously this is more than, the characters are more than 16. So when you enter, I've just added a validation statement, just to make it user interface better. And if you do not enter anything as well, like I'm not entering anything, I'm just clicking on enter right now, you get an error again. So these are small things that I've added. So yeah, you can test it once again with symbols as well. Yeah, now you can see everything is working fine. Thank you.